We are going to look at tree diagrams and independent and dependent events. So for the warm-up, how many different batting lineups are possible for a 9-player baseball team, assuming all 9 bat? And so for that one, we would have 9 choices for the first player, 8 choices for the second player, because you've already chosen one, then 7, then 6, then 5, times 4, times 3, times 2, times 1. Now, if you multiply a number by each number lower than that by 1 each time, so a situation like this, there's a name for this. This is the same as 9 factorial. So it's only when the numbers decrease by 1 every time you can do that. If we type in 9 factorial, here's what it looks like on the calculator. So we can go to 9, menu, probability, and here's that factorial, and it does 9 times 8 times 7 times 6 times 5 all the way down to 1. So that is 362,880 ways. Let me write that up. 362,880 different ways that, different batting lineups that you could have with 9 different people. Our goals today to be able to create and use a tree diagram to determine certain probabilities, understand the difference between independent and dependent events and how to calculate the probabilities accordingly, and we're going to start with tree diagrams. So let's say you flip a coin 3 times. Make a tree diagram of the possible outcomes. All right, so I'm going to say black is heads, red is tails. So here's my heads, here's my tails. All right, so the first flip, you could get a heads or a tails. All right, let's do our second flip here. And again, we could get a heads, or we could get a tails. And then let's do our third flip. And for each of these, we could get a heads, or we could get a tails. All right, so looking at our colors here, so purple, 3 blacks, 3 heads. We got a heads, a tails, and a heads. We have a heads, a tails, a tails. And we have heads, tails, heads, heads, heads. Oh, I forgot. Right in the middle here, we had heads, heads, tails. Okay. So there's the top. The bottom, we have tails, heads, heads. We have tails, heads, tails. Tails, tails, heads. And tails, tails, tails. All right, so we have 8 different outcomes. What is the probability that you flip at least, or you flip 3 heads? Well, that is 1 out of 8. And I can change that to percent or a decimal, so 0.125, which is 12.5%. What's the probability that you flip at least 1 tail? Well, that's everything else right here. So that would be 7 out of 8, which is 0.875%. Oh, that's a decimal, which is 87.5%. How are they related to each other? Well, they add to 1, or it's 100% of the possibilities. All right, to find the probability that you flip at least 1 tail, we could have done the 1 minus the probability that we get the 3 heads right there. So I could have done 1 minus the 0.125, and that would have given me all the tails. Right, so if you take a look at these two, there's a special name for these. It's called the complement. The complement to A is everything that is not A. So complement is everything that is not A. All right, so rolling a 4. What's the complement of rolling a 4? Not rolling a 4. What's the complement of flipping a head? So it'd be flipping a tails. Was the complement of making a basket? Not making a basket. Right, so either it happens or it doesn't. The sum of the probability of an event and the event not happening is 100%, or 1, or 100%. And we'll take a look at complement throughout the units, because sometimes it's faster to calculate the complement of an object, or of a probability. All right, let's draw another tree diagram. Let's say SLP and Hopkins are tied, and Anna is at the free throw line with 2 shots to make. She generally makes, okay, so 2 shots to make. She generally makes 63% of her free throws. They're independent. Draw and label tree diagrams. All right, so let's do that. She makes it in black, and she misses it in red. Okay, so here's the first shot. She has a 50% chance of making it. No, not 50 in this case. It's 63% chance of making it. Let's change that. Okay, so 63% chance of making it. 100% minus 63%. So the complement, 1 minus 0.63. She has a 37% chance of missing it. All right. She gets 2 shots. Okay, so here's her second shot. I'll do it blue. Okay, so for a second shot, she can either make it, again, a 0.63% chance of making it, or she can miss it, and each of those is 0.37. Okay, notice a few things. Number 1, if they come off the same dot, they add to 1. These add to 1, these add to 1, these add to 1. So if they come off the same dot, they add to 1. And then the probability of these, so here's that she makes it twice. Here's that she makes it, but then she misses it. Here's that she misses it once. Here she misses it twice. You might want to use different letters in your notes if you don't have different colors. Okay, so the probability of each of these happening, we would multiply along the branches. So again, if they come off the same dot, they add to 1. These are 100%. Each of these are 100%. But the probability of making it twice, you multiply along the branches. So 0.63 times 0.63 is 0.3969. If we go this way, make, multiply 0.63 times 0.37, and that is 0.2331, a 23.31% chance of that happening. Same thing here. So again, multiply along the branches. And the probability that she misses both, you multiply 0.37 times 0.37, and that is 0.1369, which means she has a 13.69% chance of missing both. These are 23.31% over here. And the probability she makes both is 39.69%. They should all add to 1. So at the end, they add to 1. What's the probability she misses both shots? 13.69%. Probability she makes both shots? 39.69%. The probability that she makes at least 1 shot. Okay, so at least 1 means she can make both, or at least 1. So we're going to add those together. A faster way to do it, though, is the complement. We know that adds to 100. So let's just subtract the probability that she misses both. 0.1369, and that would be 0.8631, or an 86.31% chance that she makes at least 1 shot, which means that they also win the game. Okay, so if she makes both shots or 1 shot, they win the game. Again, a faster way to do it is we could add these 3 together here, but we could also take 100% minus the probability that she misses, is 13.69, which is faster. So there's an example of complement. So SLP, 86.31% chance. They win. Okay, example 3, a national advertisement says that puffed barley cereal toy contains, or a cereal box contains a toy, and the toys are distributed equally. Ruthie wants to collect a complete set of the different toys from the cereal boxes. Draw a tree diagram showing all possible outcomes if Ruthie gets 2 boxes of cereal and there are 2 different toys. All right, so here's box 1. She could get this toy, or she could get this toy, toy 1, toy 2. And then here's our second box here. And again, she could either get toy 1, whoops, or she could get toy 2. Again, it's 50% for each of these happening. All right, so I'm going to write what happens here. So this is toy 1 and toy 1. This is toy 1, I'll call it, and toy 2. This is toy 2, and this is toy 2 twice. And this is toy 2 and toy 1. All right, so here are the different outcomes. Okay, what's the probability she will find both of them in her box? Well, if you take a look at this, is 2 out of 4, or 50%. Okay, if we were to multiply along the branches, 0.5 times 0.5 is 0.25 for each of these. And again, if you add them up, that equals 50%. Okay, say there are 3 different toys. What's the probability she got toy 1, and then toy 2, and then toy 3? So that's this way. It's 1 out of, if we count all of these, it looks like it's 1, 2, 3, 4, 5, 6, 7, 27. All right, that as a percent would be about 3.7%. What's the probability she will have all 3 boxes, or all 3 prizes after her first 3 boxes? Those are all the blue lines that you see. So if I count the blue lines, 1, 2, 3, 4, 5, 6. 6 out of 27, which is 22% about. What's the probability you don't ever get the first toy? So we would count, let's use green. All right, so not toy 1, so toy 2, 2, 2, so these would work. Toy 3, okay. Toy 3 this way, and going this way. So 1, 2, 3, 4, 5, 6, 7, 8 I count. 8 out of 27, which is 29.6% chance you don't ever get the first toy. Okay, the last example. Remember, if they come off the same dot, they add to 1. So these add to 1, these add to 1, these add to 1. These should add to 1 as well. Okay, so if they come off the same dot, they should add to 1. Oh, actually, the last 2 don't. Okay, so same dot, add to 1. And then remember, if you multiply along the branches, so if we go this way, we get the end number. So let's start at B. 8 times what number is 24? Well, that would be 3. So this would be 0.3. Let's do A. Again, these 2 should add to 1. So 0.8 plus what number gives us 1? So that would be 0.2. 8 and 2, 10 or 1. Okay, so then where would I go from there? Let's see. We could figure out C. So again, these 2 have to add to 1. 3 plus what number is 100%. 30 plus, I should do it in percents. All right, so 30% plus what percent gives us 1? That's 70%. So this is 0.7. Multiply along the branches to get this. This is 8 times 7, which is 56. Okay. Here, 2 times what number gives you 18, and that would be 9. So that's 90%. This is 90%. 90% plus what percent gives you 100%? So this is 10%, because these 2 add to 1. And then multiply along the branches here. 0.2 times 0.1 is 0.02. Okay, so again, lots of writing here. Let's erase some of this. Okay, so again, if you multiply along the branches, you get the end number. If they come off the same dot, they should add to 100%, which they do. And lastly, these 4 right here should add to 100%, and they do as well. Okay, so there it is. Multiply along the branches to get the end result. If they come off the same dot, they add to 1 or 100%. Okay, the rest is your assignment. So you can try this.